Thank you so much, everyone, for coming. Most of the introduction has already been done, so we can jump right into the talk. I just learned, someone told me that the talk level, it says all levels. So I hope I can provide some sort of introductory material about what we're doing, and then probably the last 10 to 15 minutes we'll go a bit more into the details of the opportunities and challenges when building AI for autonomous flight. So yes, I want to tell you a bit about autonomous flight, and this is a data science conference. We talk a lot about machine learning and what are some of the challenges that we face when we build a machine learning system that goes into production in a high safety critical environment. And so we believe that autonomous flight really has the potential to solve some of the world's largest traffic problems. Let me first see if this works. Right. So I'm sure many of you have seen some of these, at least, from the volocopter to the Lilium. There are now more than 100 companies out there that are really in an extremely interesting race to bring their aircraft to market in the next couple of years. These aircraft, there's also the Jetsons in the middle, if anyone recognizes. These aircraft are now becoming a reality, mostly thanks to advances in battery technologies. So over the last couple of years, we have seen that batteries have become better and better. At the same time, their cost has reduced significantly. And this is great because electric, means it's simpler. And if we look at it from an engineering standpoint, simpler almost always means that it's cheaper and also more reliable. We can better understand what's going on. And also, which is a really practical advantage of these aircraft, is that they have smaller propulsion systems. So, they are really meant for situations in urban traffic where, you don't want to have a big helicopter flying over your head and making all sorts of noises. Now, for any of these to become wildly successful, they need to be operated at scale. And, it's quite surprising, but there is already a shortage of pilots out there. If we now have this scenario where there are hundreds or potentially thousands of these aircrafts that we call eVTOLs, electrical vertical and takeoff landing aircraft, such as the volocopter or the Lilium, flying over cities, we really need more pilots that can steer these aircraft. At the same time, again, bringing this picture up in our minds again, we really need better pilots where suddenly the traffic is much denser and arguably there's much more going on around you, and your demand for situational awareness, which we talk about later when we go into more of the details again, is really increasing. So we do not only need more pilots but also better pilots. There's a completely other viewpoint you can take to this, which is that there are, in a Lilium or in a volocopter, there are 2 to 4 seats. So the cost of the pilot broken down on the passenger is suddenly much, much higher. So if you have a 2-seater aircraft and you can suddenly fill up 100% more capacity by removing the pilot, that's pretty. There's large financial opportunity cost there. So for us, the solution and I guess the reason for our existence is pretty clear, is that we believe we need to take the pilot out of the equation and take it with a pinch of salt, but I hope by the end of the talk you will see what I mean. The pilot really has to become AI. So here's what we are really working on. Our mission is to build a fully autonomous autopilot that can clearly outperform the human in each and every dimension when it comes to flying, with as few changes as possible to the rest of the system. So if any of you are working in aviation or have ever worked on a related project, you may know that integration with existing aircraft, for example, is really difficult. So we want to make sure that we can integrate our system with as little changes as possible to what is already in the system or what the Lilium or the volocopter will be built with as few dependencies as possible. In other words, that means we want to build a very simple system, again, from an integration standpoint. And also, this now brings us to sort of the meat of this talk within the rules of certification. And we started 3 years ago by solving what we think is one of the most difficult problems, and that is using a camera system and computer vision algorithms to replicate the functionalities that the human visual cortex has to perform in the cockpit these days. So here are a couple of pictures to really give you sort of an impression of what this looks like. This is our system mounted to a variety of aircraft. On the top left, we have a super awesome drone called the Wingcopter. So we don't manufacture any of these. We just mount our system on these aircraft. So the Wingcopter is an eVTOL drone, so it can take off vertically and fly forward at pretty high speeds, and then land vertically again. You see the two cameras pointing down there at the underneath the drone. We have an R66 helicopter in the top right, the volocopter in the bottom left, and then a typical general aviation Cessna in the bottom right. So really, the system comes down to a range of cameras around the airframe. The system is designed in such a way that all the emergency functions that the pilot has to perform, or would have to perform in our case, that the system has to perform, can be done with a single camera. And if we now look for the full functionality of the autopilot during normal operation, and also to account for redundancy and everything else that we need to take care of, we probably look at a dozen cameras, so 8 to 15 cameras in operation. I mentioned that the system is relatively airframe agnostic, so we really see this as plug and play. So you can put the system on any aircraft. The reason why we can do this is because the low-level integration is done by the manufacturers, and we take care of the high-level decision-making and perception that the autopilot has to do. So to give you the other perspective, this is what our system sees when it sits on the nose of an aircraft, here trying to land at a runway for general aviation. So we're sitting in a Cessna looking forward. And this is our visual landing system. So what we do is we locate the runway and position ourselves relative to us. Now this runs purely on vision. There's no GPS in there, there's nothing. All the system sees is the camera image that we also see here. And the aim for the system is to get sub GPS precision. So we want to be better than GPS. GPS, in most cases, is great, but not too accurate. So what we see here is, I can play it once more. We see a bounding box that shows us where the runway is. This is completely unfiltered, the prototype I built for this presentation. And we see a confidence score, how sure are we that that this is really a runway that we're looking at there. Obviously, we need to keep track of lots of other objects that are also in the air, so we give out an object ID here, which is, it says it's a runway. And then for those that may have been in an aircraft before, the bottom right is sort of an ILS, instrument landing system equivalent, that gives us the relative position to the center line of the runway. And it tells us if we have to go a bit more to the left, a bit more to the right, to make it there precisely. Now, looking at this demo and also the experience we've gathered over the last 3 years. Yes?
Yeah, on the previous slide, I have a question.
Sure.
If it's purely based on the image, what happens when it's foggy or it's rainy?
Good question. So we are focusing.
Could you repeat the question for the crowd, please?
Right, sure. So I'm repeating the question. What happens, so if this is based purely on vision or on the images that we see, what happens if it's foggy, or to take it even more extreme, what do we do at night, or during really any other bad weather conditions? So if any of you are interested in becoming a pilot, I want to fly for British Airways or any of the other big ones, the first thing, regardless of what sort of pilot license you want to obtain, is you have to be able to fly in VFR. And VFR are the visual flight rules, and there's a subset which is VMC conditions, or VMC, and that means you only fly during good weather conditions. So this is also what we are doing. So we are first looking at VFR in these visual conditions where we can fly reliably, and as a second step, we will also look at how we can integrate other instruments to be able to fly in conditions where there's that are worse. So for now, we are looking at good conditions where we can get a visual reference to the runway, for example. But but you're highlighting obviously a really good point, which is that conditions can still change. So this is what we will focus the second part of this talk on. Thanks for the question. That's great. So I was saying that the experience we've acquired over the last couple of years really shows that we will not get to full autonomy without AI. That's pretty clear to us, not only to us, also to other people in the industry, and very importantly also to the regulators. So in addition to that, I think the system already today can give quite some advantages to aviation, existing aviation, to make your journey of flying safer. So aviation provides the safest mode of transport, to just follow up on this, and that is for good reasons. Everything that flies out there is extremely tightly regulated, and has to go through several layers of certification before you can put anything into the air. So from the jet engines to the entertainment system on board, but also all criticality levels, everything is scrutinized by the FAA or EASA in Europe, the regulators that make sure that what flies is safe. So the bottom line here is that when we introduce new AI technologies, we have to make sure that this level of safety is not compromised. So how does such a system actually look like? I think this puts a bit more clarity on what this visual landing system that I've just shown looks like in detail. Again, this is really all it is in operation. We have a camera that feeds us images. We do some pre-processing. I guess many of you working in the field see this as sort of a very standard pipeline. Pre-processing does all sorts of things, from rescaling the image to doing contrast enhancement and standardization. We feed this to a convolutional neural network, and we get a prediction for an image frame. And then we feed this into some post-processing where we can sort of establish time dependencies. We can look at what happens in between frames. We can worry about all sorts of things such as false positives, false negatives, and then we do some bookkeeping around making sure that we can keep track of everything that's around us, and we have sort of situational awareness 360 degrees. For the purposes of this talk, but also when talking to regulators, it really helps having this sort of diagram. So we simplify, the production system looks a bit more complex, but if we want to reason about how to build machine learning systems for safety critical applications, it really helps to sort of simplify it down to what we see here. So this is really everything. The system also during operation is non-adaptive. So there's from regulators, there's often the worry that your system may change during operation. We don't do that. I cannot give any guarantees. What happens if we do any form of adaptation during or any learning while it's in operation. We have no recurrent connections inside this network, which makes it also a lot easier to reason about what's going on. And we also assume that the operation is completely deterministic. Now, before I go to your question, the last thing is that this is also in some contrast to some of the questions I sometimes get, which is do you use like reinforcement learning to learn how to fly an airplane? That's pretty cool and interesting, probably a nice project for a hackathon. But there's no way, from our conversations with regulators, there's no way we could ever reason or give guarantees about the performance of the system during operation if we have something where camera images come in and control commands for the aircraft come out. So we are really trying to isolate the machine learning system to the orange or reddish box that you see on here, and the rest is classical software. You had a question.
How do you explain to a regulator how your model works?
Right. Let's see if my talk answers this for you, and then if not, I'm happy to talk about it more afterwards. Right. And so when I was preparing this presentation, I thought it would be interesting to look at what it generally means to build safety machine learning systems for safety critical applications. So for those that are here and are not working in aviation, I think it's still, so I feel people can learn a lot from, or get a lot of creative ideas on how to improve machine learning systems more generally. So what I wanted to do is I wanted to take a look at sort of common pitfalls. This is also something that we started with, is let's actually sort of look at the a common machine learning pipeline and see what are things that can actually go wrong. And then I want to provide 2 examples afterwards of how we are trying to fix things or uncover things. So we start with data collection. There's a whole bunch of things that can happen here. And keep in mind, this is all in a safety critical context. There's no room for error. So some of these are actually quite involved, whereas they might look quite simplistic at first sight. So collection errors, you might just go out with your aircraft, collect data, and you come back and there are like all sorts of black and white stripes over your image. So you have pixel loss, you feed this to your machine learning system, God knows what happens to this. Data biases, we have a couple of pilots in the company. They tend to always fly the same routes, I would assume. So if you end up collecting data and you sort of have your personal preferences, you're very likely that you're actually introducing biases. Traceability is a big thing. So we actually need to, I've gone to some of the ML Ops talks at the conference here, which are great, where people talk about productionizing machine learning systems. We really need to be in a position where we can trace everything back from the model to when the data was collected. So we need to know, who collected the data, what were the sensors involved, where was the data stored. If the data was ever moved, we actually need to, sort of record that move of the data. If there are any data augmentations going on, we need to make sure that this is recorded. So really, when you get a model at some point, you need to know exactly which data samples were used to train that model, and how do these data samples trace back what we call back to birth. So, when they were first recorded. And then there's a more obvious one which I wanted to put on there for completion, which is that your data ingestion pipeline might simply corrupt the data. Data annotation, very interesting one. So, the first thing that we always say is, well, we will just have 20 people annotate the same image, and then we can measure disagreement, and we can look at all sorts of things, and then we just reject it or re-annotate it or look at it ourselves. Now, I just yesterday spoke to a colleague who worked on a big machine learning project prior to this company. He said they had 19 people annotating the same image, and it was still wrong. So, thing here was that the common mode was the spec that went out to the people annotating. So that's something that we often forget, and something that we've also made quite some experience with over the last couple of years. Is the specs to data annotation are really critical. Then there are obviously errors that can always appear, and we need to manage them. We'll first be able to detect them and manage them. And then a really interesting one is actually annotation biases. So, we had data collection biases, now we have annotation biases. So this is really, there is a chance that all of us in the room look at an image and we think that we see something else than that's actually on the image. And, there might be all sorts of factors in there. Maybe we are an interesting, selection of people, which I'm sure we are. Maybe we all look at the image through the same screen, and so the screen might obscure some of the facts. There are all sorts of interesting things around, making sure there are no biases in annotation. And again, we need to be able to manage them. Now, training is obviously a big thing. So, many see this as sort of the core of the pipeline, which also makes it a bit dangerous because you forget about the boring data collection and the annotation. Again, for safety critical stuff, is no compromise. So the learning process can simply be incorrect. I might try to optimize my model. I end up in some local minima that some funky things when in operation. All sorts of things. I might have chosen the wrong loss function. training data set is not representative of the use case. This is one we will look at later too. If I obviously want to detect runways and I only train the network on birds, I have very little chances of actually recognizing the runway. Now, this is an extreme example, but as we will see later, this is actually quite fundamental, and there's quite some work in making sure that our data sets are representative of the use case. Then there's the bias variance trade-off, which I'm sure many are familiar with. We need to be able, even if we can't avoid it, we need to be able to measure that. And then, training reproducibility and also common mode failures, where again, the last one I think is often overlooked, but we tend to just, push things onto the cloud and train the same model 20 times on the same GPU. Well, what if the GPU has, introduces some form of erroneous behavior in the model? So we really need to be sure that we can eliminate common mode failures. Similar for the popular deep learning frameworks that everyone uses. You tend to train your model with the same framework. What if there is an issue with that framework? Maybe it's a good idea to actually train your model with two. Evaluation. So wrong choice of evaluation metrics. Maybe you can even phrase this a bit more lightly and just say, or in the positive way, you have to find the right set of evaluation metrics. This is really tricky. How do you, not fool yourself and give an honest opinion about the performance of your model? That's something that we are spending quite a lot of time working on to make sure that we can give an honest evaluation that really captures all the aspects of our use case. We have the equivalent again, that this test set is not representative. Again, we'll look at this more later. And then there's a whole area around detecting edge cases and improbable events. So, I really want to make sure that I take into account what I might consider not to be so lucky in operation so that the model doesn't get thrown off. Now, also in preparation for the second part of this talk, there's a note to make here. So really, when we, in most machine learning projects, if not all, when we talk about generalization, then that sort of, what we establish there really comes from what we define as held out data sets. So that's actually quite important. We say the model generalizes, this is the performance of the model, but really I think we often underestimate how much sort of our own subjectivity and definitions go into that. And then operation, I think there are quite a few terms here that you're familiar with. So we need to be able to either detect or even better handle out of distribution samples. There's the popular topic around adversarial attacks, which we just had a discussion over lunch about. Some people said it's just an interesting research problem. Other people said it's actually real danger for the system. Whatever it is, we need to eliminate that uncertainty to make sure that the model cannot get fooled. I mentioned earlier that we don't do online learning. It's just much harder to reason about that if you have 10,000 of these flying in the air, 10,000 models training on the fly with different impressions. I've got no idea how I can convince anyone that all the stuff is working out there. So what we do is, again, we fix the model after we release it, and it doesn't change. We even have to go through what is called recertification if we want to put out a new model for an upgrade or something. Non-deterministic inference. So the GPUs that are mostly in use these days are actually pretty non-deterministic, which people don't notice in sort of everyday applications. But if you want to have formal guarantees about your performance, then that's not good. And then model behavior is not explainable, so that's also a problem because if things go wrong, you do want to be able to find the root cause of the problem and then be able to address that. So really, if you think about it, and I want to sort of go to the second part of this talk, which is how can we convince people that the model is safe before we've actually put it into operation? I guess this is, again, nothing specific to what we are doing. It's very common for any sort of machine learning project is, all your evaluation, all your performance, in quotes, guarantees are, actually done before you put the system into operation. In aviation, we call this design phase and operational phase. So everything you see in blue here is the operational phase. The design phase. We don't have access at this point to the operational phase. We can do as much testing as we want, but when the things are out there, we need to show before that everything is safe. And again, just to reiterate, everything after evaluation, the model is fixed. We don't do anything to it anymore. We will just have it run in operation. So what I want to look at is how do we actually establish operational performance guarantees before operation? Sounds like a chicken and egg problem. But I think that's very common to all sorts of machine learning problems out there. A couple of thoughts on this. So it's probably good to start with a couple of error metrics. To say anything about how our model performs in operation versus the data sets that we have in the lab that we can test on, it's probably a good idea to define a couple of errors, including what we call the in-sample error. So this is the error you can compute on the data sets you have in the lab, data that you have collected previously that you can evaluate your model on. And then there's the hypothetical out-of-sample error. So this is really what we encounter when we deploy our system on the aircraft and it goes out there and flies. So I think what you see there at the bottom is a very common observation. So your error on the training set is smaller than on the validation set, than on the test set, and then it's smaller than on the out-of-sample error. Now this doesn't really help us at this point because it's actually no good news. So what I want to show is that I can make the statement that we see at the bottom, but at the same time I can make sure that the bounds are extremely tight, so that all these values sit very close to each other. And so how do we do that? That's the big question. So let's maybe take a closer look at how we do that. And the first thing we observe is that the out-of-sample error actually we sample from this big X that if you don't sit too far away, you can probably see. So what is that X? So I called it a hypothetical error, and we sample from a space. It's called X. What is it? Well, we can start by maybe saying that it's it's an input space that describes all the 512 by 512 RGB images that you could ever possibly record over Switzerland. So this is, we sit on an aircraft, we fly around, and we collect all these images. Now what we realize about this is that it's very easy to talk about this space. Now I've just given you a definition of what this space is, but it's actually very hard to characterize this mathematically. So in addition to knowing our input space, some of you may remember from statistical learning theory lectures, what goes into the direction of VC dimension, that actually tells us that for a given class of model, a training data set size, and in a failure probability that we can really define or make arbitrarily small, this is what we would define for an operational use case, meaning your model cannot fail more than 0.01% out of all times. And then an arbitrarily small interval around the training error that you observe, so this is the in-sample error, we can actually come up with guarantees that then our error during operation lies within a certain interval around the error that we observed during training. Now there's a big if. And the if is that the distribution of the data that we train on needs to be close to the distribution of what we see during operation, which I think intuitively makes a lot of sense. Now, the inference data here, or the distribution we see during operation, I also mentioned that's pretty hard to characterize. So how do we go about this? Well, the first good idea is to reduce the dimensionality of that space. So we come up with a couple of operating parameters that define our operational scenario. So we look, for example, at if you think back to the runway or the visual landing guidance system, we can define a couple of parameters that define this scenario pretty well. One is, for example, our angle of approach. The other one is the time of the day. The other one is the speed, and you can come up with all sorts of other things that are relevant to your use case. This is actually something that's done in aviation, or has been done for decades. So when you want to build a jet engine and certify that, you come up with the exact same parameters to test your engine in different conditions. Now, this is all nice. We end up with something that you see there on the right. In this case, a three-dimensional space, and we can plot our data points along these. So this is actually one of our data sets that you see there. Now, again, we want to show that our training set distribution is the same or similar to the distribution we observe during operation. Now, the first step I would probably do at this point is to say, well, we show that our data sets that we have in the lab are independently distributed in this operating space. So this is the simplified space that I have there. Now, if you think about this for a couple of minutes, you probably realize that this is not enough. I can easily come up with conditions and combinations that are actually not representative, and I don't observe particularly often in my original input space. So, in addition to that, I need to show really what I wanted to do from the beginning, that my data sets are sampled independently from the input space. Now, we remember that it's very hard to characterize that mathematically, so we come up with a proxy for that, which is that you come up with what we call an input distribution discriminator that provides you with a likelihood of how likely it is that your samples come from that input space. So then, if we do that, I can use that during operation, and I can use my predictions as long as this input distribution discriminator gives me yes, 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 you are in that input space. I know that I will perform well given my equation at the bottom, and I have tight bounds around my errors. Now, we have a complete data set at this point, and we can come up with all sorts of guarantees about our performance during operation. The question that we often get is, this is nice, but how do I show that my model is robust to input variations? And so I want to spend the last couple of minutes talking about how we do that, in addition to what I've shown before. So if you train a model normally meaning you use gradient descent and have a data set that you train your model on. In this case, we even have a few data augmentations in there. If I now take an input sample and I push that through the image, through the network, and I look at what my representations inside the network look like, I can characterize these. And if I now make changes to that input, so I change the viewpoint, I change the brightness, I might make some other perturbation to the input, I can characterize or quantify how much my intermediate representations change. What we see here intuitively is that for this particular network, if I make changes to my input, my intermediate representations change quite a lot. Now, people say, oh, you can do this thing called adversarial training. So if we look at it, it actually becomes a bit better. So we've trained the model adversarially. You see it becomes a bit better. We still have quite some amplitude there, but the means you see are significantly decreased. Now, this is great. The problem with adversarial learning, really, if you think about it, is we cannot prove anything here. We're introducing these adversarial samples during training, and then we're hoping for the best during operation. So we have to go a step further. And I won't go into details of this, but we are pretty much looking at training our models in a provably robust way. So over the last couple of years, there have been made improvements to sort of the traditional SMT solving techniques for neural networks, where you can exhaustively show that your models are robust, but unfortunately they don't scale very well for sort of large neural networks that we are looking at. method called interval bound propagation, proposed by the guys at DeepMind in 2018. Sort of relaxes all of that a bit. And here what we see is, gives it an intuitive idea, is that we have our input image and we construct a ball around that input image. So then that ball represents changes in viewpoint that you might see, or changes in illumination. And then what we will do is we will push that entire ball through the network, and we will verify that the output is completely classified, or still gives the same class for every point that we get. Now, there are a couple of problems with this. We end up with a pretty big optimization problem, and to be able to efficiently solve that, we do some approximations. These approximations work unless you have very large networks, or also your perturbations become very big, which we have here. And then you see that these bounds do not become so meaningful anymore. So we're doing quite a lot of work now on finding better ways to maybe go a bit closer again to exact propagation through the network. Pretty much, can we find better approximations of what we call polytopes, these intermediary balls, through the network to better approximate the shapes, and then have a better understanding when the ball comes out of the network. If we do that, so this is now again the same model trained, we get a much more robust representation of the model. And we can actually guarantee that up to some point there's almost no change in their representation. Now the use case for this is that, again, we're going back to the runway example, is that we can construct certain, we can vary the viewpoints around the image, and we can show what you see on the right is, for example, maximum brightness and minimum brightness at the top, and then you have rotation towards the right. So we can provably show that our networks are robust to any changes within these intervals between the min and the max of these dimensions. And so all of this is part of a bigger story, and that we are working together with EALSA to sort of provide a first set of guidelines around how we can make machine learning systems, or specifically in this case neural networks, safe for use in aviation. And I'm not supposed to advertise anything, but if you're interested in this topic, and I really do think this is relevant beyond our work, we will publish a white paper or a summary at the beginning of 2020, and I think this can help in industries such as healthcare, medical applications, pharmaceuticals, autonomous driving, obviously. But I also think that many of the ideas really help us, or have helped us actually build better machine learning models from a more general perspective. That's my last slide. We are based in Zurich. Right, if you have any questions, feel free to get in touch via email, or we've got 5 minutes left to answer any of your questions that you may have.